In the framework of C-Service project, deliverable 6.1 aims to provide replicable eco-design guidelines for the sustainable production of electrical and electronic equipment. The guidelines include the following section: Introduction to the eco-design of electrical and electronic equipment, including key aspects and eco-design principles, the role of the design in the electrical and electronic sector, as well as an overview of the C-Service project and its main objectives. Methodological approach for the integration of eco-design into EEE production, description of the identified eco-design strategies and their validation through examples of successful implementation of the eco-design strategies and best practice from electrical and electronic industry, and finally application of eco-design strategies to C-Service case studies. Several eco-design strategies can be applied for an environmentally compatible design of EEE to prevent and reduce environmental impact of product throughout the life cycle phases. The table shows all the eco-design strategies for EEE that have been identified based on literature review and validated by C-Service partners through the survey conducted within Task 6.1. In the following slides, each eco-design strategy is briefly presented. Concerning the development of new concepts, it foresees the implementation of innovative strategies such as dematerialization, multifunctionality, and development of new services into product design, ensuring that the device fulfills all consumers' needs. While physical optimization aims to increase the reliability, durability, and functionality of the product, improving its environmental performance. Eco-design can also help in the selection of suitable materials at the design stage, thus reducing the use and consequently the depletion of critical raw materials, such as rare earths, precious metal, cobalt, tantalum, indium, gallium, and limited resources, while at the same time increasing the probability of reuse and recycling at the end of life. Instead, the production process could be optimized to improve the environmental performance of the product by improving process efficiency, reducing resource use and waste generation, adopting alternative processes, increasing internal recycling, and fostering the use of renewable energy systems. The distribution phase can be optimized by acting on packaging, reducing the amount of packaging and resources and associated impacts, and enhancing transport, for example, optimize each shipment, selecting best transportation mode, reducing packaging size, as well as improving the logistic network. Regarding the use phase, the eco-design strategies focus on the optimization of product use to reduce waste generation and consumption of energy and consumables. The end-of-life phase can be optimized by facilitating the end-of-life management, encouraging options such as recycling, reusing, and remanufacturing. Finally, the use of ICT tools for communication and information exchange throughout the EEE value chains can be important to significantly enhance circular economy aspects in the electrical and electronic sector. Several case studies listed in the box from an electrical and electronic sector are reported in the guidelines to validate and identify strategies and demonstrate real-world strategies and best practice, as well as to prove the environmental and commercial benefits that can be achieved by applying eco-design strategies in the electrical and electronic equipment. The table shows an overview of eco-design strategies implemented in the respective C-Service case studies. The following slides focus on C-Service case studies developed within Work Package 4. Different eco-design solutions were applied to the target products. Such eco-design measures were derived from the first circular economy business model focused on C-Service target products developed in Work Package 2. The table shows the eco-design actions that were implemented in C-Service washing machine demo and related environmental benefits. The first action is the reduction of polypropylene using blowing agent, which entails less plastic usage and lower CO2 emissions, weight reduction and lower energy consumption in the use phase, thanks to the increased productivity. The second one is the increase of the recycled plastic content in washing machine parts, entailing less environmental impact by using recycled raw material instead of virgin materials, and high potential cost savings due to the use of recycled plastics. Then, the use of ICT tool for tracing the recycled content, thus enhancing product circularity. QR codes were integrated in products so that consumers can access via app to information about the sustainability and circularity of the product. Another action is the development of eco-leasing model for corporate washing machine customers. The company takes care of maintenance and repair service as well as the end of life of the product. Finally, the C-Service demo products will be reused to give them a second life, reducing environmental impact due to the enlargement of product lifetime, as well as the resource consumption, waste generation, and related costs. From the result of repair and recycling operations, potential eco-design measures can be drawn to be further implemented by Arsenal by the end of the project. For the printer and toner cartridge demonstration, the activities focused on the analysis of the selected Lexmark printers and toner cartridge in order to determine potential eco-design measures to be implemented in future models in terms of material circularity and recyclability. All the eco-design actions are reported in the table. The first action is design for recycling, an analysis of potential improvements based on the collaboration with the recycler to implement design for recycling was carried out, entailing a reduction of resource consumption and lower greenhouse gas emissions by the extension of a product life cycle. Then, the use of ICT tool to improve circularity of the printers and toner cartridge was investigated. That means improving tracking of printers and information sharing across the value chain. Furthermore, design for remanufacture was explored. The potential for expansion of the printer refurbishment activity was analyzed, taking into account cost and customer acceptance. The extension of product lifetime reduces CO2 emission as well as resource consumption and costs of the manufacturing process. Finally, the increase of the resource logistic efficiency by the extension of the current LCCP platform and by the adoption of the new ICT platform developed within C-Service project for the optimization of logistic operations. This led to a reduction in unnecessary and incorrect shipment, lowering CO2 emissions and costs associated with them. For the ALM demo, no new active units are being developed within the project timeframe due to the time constraint. However, another internal eco-design guide will be released by the end of the project, containing potential eco-design strategies to be implemented and new recommendations derived from the demonstration experience. All the eco-design actions are reported in the table. Manual disassembly of ALM units and the XFR analysis of plastic parts derived from disassemblies were carried out to investigate the suitability for an easy disassembly and recycling. New fiber optic sensors were developed to substitute the conventional electrical sensor. This eco-design solution is more energy efficient and offers a longer lifetime and increased reliability and sustainable design. Therefore, thanks to the higher lifetime and energy efficiency of this new sensor, the total environmental impact is significantly lower than the electrical sensor. Other eco-design measures are the use of more efficient resources in sectors other than ICT that are enabled by ICT solutions, and improving packaging by developing new plastic-free packaging and tape, entailing less plastic usage to reduce plastic pollution. And finally, PSS selection combined with the lifetime optimization study for ICT products. This leads to reduced environmental impacts due to the increased producer responsibility in terms of sustainability and to the optimization of the product life cycle. All the eco-design measures that were implemented in the C-Service TV set demo are the following: increase of recycled plastic materials in TV backover, reducing the virgin raw materials consumption, introducing reusable packaging, namely multi-use plastic boxes instead of individual cardboard packaging in forward and reverse logistics, decreasing packaging waste. Furthermore, reusable packaging has cost advantages and uses less carbon than styrofoam. It offers better protection of the product, reducing the transit damage. Then tracing of recycled content via ICT tool, enhancing product circularity during the production and end-of-life phase, and developing of an eco-leasing model for corporate TV customers. And finally, the C-Service TV demo product will be remanufactured and reconditioned, reducing environmental impact due to enlargement of product lifetime. In conclusion, the guidelines provide a list of eco-design strategies and best practice from electrical electronics sector that can help designers and manufacturers of EEE to improve the sustainability performance and circularity of their products. More widespread adoption of such strategies and practice will be the key to prevent and mitigate the environmental impacts associated with the rapid growth of EEE products. And C-Service case studies represent a practical example of how eco-design strategies can be implemented in the electronic electric sector. And finally, the eco-design solutions that were applied or explored in the four demonstration products are in accordance with the generic strategies for eco-design in the electrical and electronic sector and seem promising in terms of contributing significantly to strengthening the circular economy in the sector. Their effectiveness in terms of sustainability will be validated in Work Package 5 by the end of the project.